This is part 6, Backpropagation, of the series AI for Everyone. Have you ever wondered how an LLM learns or how we train a model to become so smart? It is done through a process known as backpropagation. Backpropagation is used to train or fine-tune LLM models. When Frank Rosenblatt introduced the perceptron in 1958, one of the biggest challenges was the lack of an effective method to train a multi-layer perceptron, MLP. This problem remained unsolved until 1986, when David Rumelhart, Jeffrey Hinton, and Ronald Williams introduced backpropagation, a breakthrough technique that enabled the automatic training of MLPs. This discovery marked a turning point, unlocking new possibilities and accelerating research and development in the field of AI. Backpropagation is the most important concept in the LLM world. This enables LLM to be trained. Backpropagation works by taking an input and comparing its predicted output with the expected output. It then calculates the error using a loss function, which helps determine how to adjust the weights and biases of each neuron to improve accuracy. This process is iterative. Small adjustments are made in each step, and the model continues to refine itself over multiple iterations until the error is minimized and the predictions become more accurate. To better understand this, consider an analogy. Imagine you are standing on top of a mountain, which represents an initial state where the output is far from the expected result. The goal is to reach the deepest valley, which corresponds to the optimal solution with minimal error. Since multiple valleys may exist, the algorithm follows a gradient descent approach, taking small steps downhill to progressively move toward the lowest point. This is achieved through mathematical optimization techniques that guide the model in finding the best possible solution. Backpropagation is the most expensive algorithm and takes lots or memory, GPU, and time. Now let's dive a bit deeper into the neuron level and explore it in detail with an example.
You can think of training a little bit like tuning the dials on a big machine. The way that a language model behaves is entirely determined by these many different continuous values, usually called parameters or weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind-boggling. This image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about it. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup.
So backpropagation essentially involved the following steps. Step 1, shuffle the data to create mini batches. Step 2, perform forward pass or prediction. Step 3, find the loss. Step 4, use backpropagation to adjust the weights and bias per mini batch. Continue doing this for many iterations till the predictions are correct. There are a few important keywords to be noted that are related to backpropagation or in general to training and fine-tuning. Epoch. An epoch refers to one complete pass over the entire training data set. If a data set has 10,000 samples and the model sees all 10,000 once, that's one epoch. Batch size. It determines how many samples are processed before updating the model's weights. Instead of updating weights after every single sample, which is called stochastic gradient descent, weights are updated after processing a batch, called mini-batch gradient descent. This speeds up training and helps prevent overfitting by introducing some generalization through batch statistics. Learning rate. The learning rate controls how much the weights are adjusted during training after each batch is processed. It is typically in the range of 0.0001 to 0.1, with common values between 0.001 and 0.00